In this screencast, I want to talk about heaps and their implementation. One of the reasons heaps are important is that they efficiently implement priority queues. Priority queues have lots of different applications, as you can see from this slide. And in particular, heaps implement both insert and remove max or min, depending on whether it's a max heap or a min heap, in log n time. This is much better efficiency than you would get with either using an array or a sorted array as the implementation of the priority queue. So let's get started. The definition of a heap is it's a binary tree with keys at the nodes of the tree, and this tree has two really important properties. One is that it's essentially complete. That means that all the tree levels are full except possibly the last level, where the rightmost keys will be missing. So the best way to understand this is through this picture, and you can see the solid part of the tree is where both any parent has both children, both a left child and a right child. And the key at each node is bigger than or equal to the keys of its children if it's a max heap. And this is called the heap property. That's the second important thing. These two things together are what make heaps very efficient. And we'll talk in the next couple slides about a little bit more about the actual implementation of these so that they're very efficient. So before we go on, let's just illustrate the heaps definition and what it sort of means for how things are stored in the binary tree. So the heap on the left, you'll notice each parent is bigger than its children, okay? But there's not necessarily any relationship going from left to right. But that's a heap. It's all the levels are full except the bottommost level, and the bottommost level is filled from left to right, and it's only the rightmost nodes that are left unfilled. The second picture is not a heap because it does not have the structure property or the shape property. Namely, if you can see that the node that contains 5 does not have a left child, and there would need to be a child there in order for it to be essentially complete. And then finally, in the binary tree on the right, you can see that the heap property is violated again by 5's left child, because 5's left child is a 6, and that's greater than 5. So that violates the heap property. Notice that if you go look at the tree on the left, the heap's elements are ordered along any path from its root to the leaf. Okay, so namely the root is the biggest, then the next, its child is smaller, the children of that node are smaller, etc. So any path from the root to the leaf would be ordered from biggest to smallest for a max heap. So this slide calls out the most important properties of a heap, and again we'll just be talking about max heaps here, that you need to remember. So for a given n, where n is the number of elements that are going to be stored in the heap, there's a unique binary tree with n nodes, right? You just basically fill it from top to bottom, and you go from the left to the right, and it will have height equal to log base 2 of n. The root will contain the largest key, and any subtree rooted at any node of the heap is also a heap. And finally, and this is what we'll talk about in a second, a heap can be very efficiently implemented using an array. So this slide illustrates how a heap is implemented using an array representation. The key thing here is, there are a couple of things here. The array gets filled in, there are no holes in it, from left to right, corresponding from top to bottom in the tree. And the indices, the second thing to note is the indices, you start filling in the array at index 1. The reason for this is it makes the operations that you're going to have to implement for moving around the tree into basically single bit implementations, either a shift left or a shift right. So let's take a look at this example here. 9 is in the root, and that's stored at index 1. 5 and 3 are its children. They're stored at index 2 and 3. The children of 5, 1 and 4, are stored at 4 and 5, etc. So if you examine this and look at it carefully, you'll see that for a node, given node J, you'll see that for a given node J, that the left child is at index 2J and the right child is at 2J plus 1. So if the index of a node is J, the children are at 2J and 2J plus 1. So that's either a bit shift or a bit shift add 1. And if you look at a node J, you'll also see that its parent is at J over 2. That's the integer, of course. And that again is just a bit shift. So that allows you to move around the tree very efficiently. Notice parental nodes are represented at the first n over 2 locations. And so you've got basically roughly half the nodes are leaves and half the nodes are interior nodes. So I want to talk about one of the important operations on a heap, and that's the insertion of a new element. So how do we do this? Well, we insert the new element after the position of the last element in the current heap. Okay, this will maintain the structure property. In other words, it's the first open element in the array, basically. Now the array is going to have more positions in it most of the time than the size of the heap, so you want to make that distinction here. Okay, then what do? Well, we've put it basically at the bottom of the tree, so we need to try to find its proper place. And that turns out to be pretty easy to do. All we have to do is compare it to its parent. If it violates the heap condition, so if in a max heap it's bigger than its parent, then what do? We basically exchange them. We drift them up. And we keep doing this as we move up the tree until the heap condition is satisfied, and namely until we're putting it at a spot where it will be smaller than its parent. So here's an example that hopefully will make this a little clearer. We're going to insert 10 into a tree here that will go in this next position right there. And then what do? We compare 10, that's what this little double arrow means. We're going to compare 10 with 8, and 10 is bigger than 8, so we have to move it up the tree and move the 8 down the tree. Okay, then we compare the 10 with the 9, and 10 is greater than 9, so we move the 10 up the tree and the 9 down the tree. It turns out we're not going to quite do that, but you'll see that later in the slides. But conceptually, this is what happened. So on this slide, I want to talk about insertion, and I want to talk about the actual pseudocode, or one version of the pseudocode that will actually work. What I want you to focus on in this slide is the loop which moves finding the position to actually place the entry into the heap. How we move up the tree in order to find that. So again, we're given an array A. We want to insert an item X. The first thing we need to do is check the heap capacity. Now this is an important point. When you're using the array, again, remember that their heap capacity is going to be determined by the size of the array. And we may need to increase that, but many times the heap will take up much less space than the entire array. And so we actually just need to be able to find the place to put it in, and that we're going to keep track of that in the heap size. So let's assume for right now that there's open space. We're going to increase the heap size by 1, okay, and then that will take the basically make the space for where we're going to insert the element. Okay, so where are we going to start? Where's the open slot that we're going to use? It's going to be in heap size, that particular slot in the array. Remember, everything's indexed by 1 here. And while whole is bigger than 1, okay, so in other words, we haven't gone off the top of the tree, and if x is bigger than the parent of the whole, that's exactly the condition. You should stop and think about this. That's exactly the condition where we're going to want to move the position up and move the parent down. So that's exactly what we do here. We move the parent down. The parent is in index spot hole over 2, and so we move it down to index spot hole, and then we move where the open position is. We make the open position now be where the parent was, which was hole over 2. And we keep doing that, right, until either we find the spot, okay, so either this doesn't hold, or we're at the top of the tree. Hole is equal to the root, in which case we insert X into the hole. So take some time, make sure you understand how this pseudocode actually implements insertion, and in particular understand this loop down here that does the drift up or percolate up. Second basic operation is to remove the max from a heap and return it. So the pseudocode for this is relatively straightforward. There's some more details later, but basically what we do is we remove the root, that's where the max is because it's a max heap, and then we take the last entry in the heap and move it to the first entry in the heap. Okay, we reduce the heap size by 1, okay, because we're removing the max, and this entry that we moved, the last entry, is now in the root, so we don't need to worry about losing that. It's just going to lay in the array, be in a position in the array that we're not going to access. So we reduce the heap size by 1, and then we drift down the first element until the heap property is restored. Now I'm going to have to talk about exactly how drift down works. It's a little more complicated than drift up. And then finally, when we get to a spot where the heap property is restored, we're going to return the original root of the heap. Okay, so there are really two basic moves you should study carefully and make sure you understand: drift down, drift up. So to remove the max from a heap, we're going to use the second basic operation again, which is drift down. So, and we're going to write this one a little bit more generally so it can be used other places, and you'll see why later. Again, it's one of the basic things that you do in a heap, and you use it multiple places in terms of implementing all the methods that you're going to want the heap to support. So here we go. It's going to be drift down is the name of the method, and basically it's past the position where we think the entry is out of place, and we think it's too small for where it is potentially. So what do? We save the value that's in that position in the heap, and we check to see if it has children, if it's a parent. And we do that, right, where its left child is going to be the one with the smallest index, and that's just going to be 2 times the position of the parent. And we'll see if that's less than or equal to heap size. If it is less than or equal to heap size, then that means that there's a child there, and so we need to check to see whether the element that was in position and is now in temp, whether that element is smaller than one of its children, and move it down. Now we have to check, what makes this a little bit tricky is now we have to check whether or not there is the left child is the last entry in the heap. In other words, does the index of the child equal to heap size? And again, remember, everything's starts indexing at 1, so you can just make this comparison without worrying about plus or minus 1 entering into it. And then we check if the right child is bigger than the left child. If the right child is bigger than the left child, then that's the one we're going to want to switch. So if the right child is bigger than the left child, then we increment child so that it's pointing to the bigger of the children of the parent. So now we check. If the child is bigger than the thing that we started out with, temp, then we're going to want to move the child up. So we do that here. We move the value that's in a child into a pos, and then we let pos, that's not going to be the new open position, we let pos be equal to the index child. If the child's not bigger than the temp, the element that we're moving, then we don't need to move it. Okay, so then we just break out of the loop and we put temp into pos. Notice you should take some time and convince yourself that this code works even when the entry that's in index pos is correct to begin with. And in fact, if it's correct to begin with, it just does these two statements, namely it puts it into temp, and then it takes temp and copies it back into where it was originally. So those are the two basic operations in a heap, basically insertion and remove the max. Now, again, if you have a min heap, then it would be insertion and remove min, and really the only difference is you just switch the sense of the inequality signs all the way through, and everything would still work, and instead of a max heap, you'd have a min heap. That's fairly easy to do in most programming languages. For example, in Java, you just change the compare to method to reflect how you actually want the elements ordered. So once we have these operations, and I'll talk some more about actually building the heap in the first place in the next screencast. But once we've got them, then we've got all the ingredients of a priority queue. The priority queue is really an important abstract data type. I mentioned it earlier, I believe, and it gets used in all sorts of contexts. We'll see it again in our course when we do shortest paths, and also when we do minimum spanning trees. But it's also important in process scheduling and operating systems. There are lots of different ways to implement priority queues. Binary trees are binary heaps. Binary heaps are the one that gets most used. Lists and sorted lists are not as efficient, so they're generally not used unless you know that you're not going to have large priority queues and you don't need the extra performance efficiency boost that you get with a heap, which appears when you have a large heap. Okay, priority queues, normally you've got a find element, a delete element, and an assert element, and then sometimes this gets enhanced, and I'll talk about this again later in the course, when you have to delete an element, or more importantly, change the key for a given element. Okay, so that's it for now. The next screencast is going to cover basically building the heap from scratch when you have a set of items and you want to put them into the heap and have the heap property be satisfied.